As promised, I am putting a video cast together for the amine chemistry section of the course. If we take a little look at the introductory page, what we've got here is a typical pharmacologically active molecule, and you can see from the presence of nitrogen in the structure, particularly here and here. These are amino-like functionalities. This is an amide here, which we'll talk a little bit about as well. This is actually LSD. This is a gamma-aminobutyric acid analog, and for anyone that recognises him, this is Ian Curtis from Joy Division. And you might want to look up the relevance of that. Okay, here we've got a brain slice, and this is showing the serotonergic pathways in the brain, and this is serotonin. And again, we've got a primary amine here, and this is a beta ethylamine-like neurotransmitter. And then here we've got adrenaline, and adrenaline is a phenolic alcoholic amine, and again a beta ethylamine type structure. They're called beta ethylamines because this position is alpha to the amine, this is beta, and then we've got a phenyl group, and this one is called a beta ethylamine like compound because it's alpha beta and then an aromatic next to here. We can make some very ready comparisons with alcohol chemistry. Amines can be regarded as nitrogen analogues of alcohols and ethers, with some obvious differences, as we'll come across. So for instance, if we take water and propanol from our previous lectures, remember I said that a way of thinking of alcohols is to think of them as alkyl derivatives of water, and then you can actually put quite a lot of chemistry just based on that fact. So as per water and alcohols, we can do it with ammonia and N-propylamine or 1-aminopropane as an analogous system. Amines exhibit similar physicochemical properties to those seen in alcohols. Hydrogen bonding can still occur between molecules in a pure compound or in solution, say in aqueous solution. Amines tend to be fishy smelling, and in fact when fish goes off, one of the reasons you smell fish is that two chemicals known as putrescine and cadaverine are produced, and these are both aminergic compounds. So here we have hydrogen bonding occurring between two alkylamines, and the hydrogen bonding will encourage the alkylamines at a certain molecular weight to be liquids. The earlier members of the group as pure amines, such as methylamine and ethylamine, are gaseous. Propylamine would be on the border of being a liquid, would be a low boiling liquid. The amines can be soluble in water, and this is why. That also means that they're soluble in alcohols, if you think about it. So just a reminder, hydrogen bonding via amino groups plays an important role in structural biology of proteins, as we've seen from the cells to systems lectures, and 3D structure of protein chains involving lysine, an amino acid side chain, an amino side chain containing amino acid, and nucleic acids, pairing of amine containing bases in DNA and RNA, albeit slightly modified amines. Amines, it's basic. Ammonia is more basic than water due to the fact that the lone pair of electrons are more available for covalent bonding than in water, since the oxygen in water is more electronegative than nitrogen. For the same reasons, amines are more basic than alcohols. Not only does hydrogen bonding take place in aqueous solution, but also proton transfer between water and the organic amine. So dissolving an amine in water will cause a basic solution to be formed, and this is because a hydrogen bonding to water and then subsequent further proton transfer can occur in equilibrium. So we have hydrogen bonding occurring, and we also have ionization occurring because the amines are strong enough bases. All aminergic compounds containing amino groups, when dissolved in water, will exhibit basic properties, and that means that often amines dissolved in physiological solutions will be protonated at physiological pHs. The consequences of this chemistry is that dissolving amines in water will cause an alteration of the colour of pH paper, demonstrating a proton concentration change, an aqueous solution becoming more alkaline. Formally, the compound on the right hand side is known as N-propyl ammonium hydroxide. Per se, these compounds are certainly not stable. You can't isolate primary amine hydroxides readily. That means that amines are also soluble in acids like ammonia, they would dissolve in aqueous acids like hydrochloric or sulfuric acid readily. And the reason why they would do that is that you have H3O plus in solution, and that will transfer the proton from H3O plus to the amine, giving water and a counterion. If the counterion is chlorine, that would be hydrochloric acid. If the counterion is HSO4 minus, that would be sulfuric acid. The position of the equilibrium, how basic the compound is, depends on the nature of the carbon-based substituents attached to the amino group and how they affect the availability of the lone pair of electrons on nitrogen. So that means that there are steric and electronic effects, both inductive electronic effects and conjugative effects on the nitrogen lone pair that can change the basicity of amino compounds. Just a reminder about the web links here for further reading, particularly on things like nature of the carbon-based substituents and their effect on basicity. Background reading for amine chemistry within textbooks is highly desirable. Okay, so we're going to forge ahead. We're going to look at something that hopefully will engage you. So here what we have is, this is actually crystal meth. Okay, so this is methamphetamine and it's crystalline or white crystalline solid, and the way that chemistry is done in clandestine ways, illegally, is that a compound called P2P, it doesn't matter what that formally is called, although you should be able to name that IUPAC wise, P2P can be reductively aminated directly to methamphetamine, or it can be obtained by what's called the Leuchart reaction, and the Leuchart reaction goes via an amide onto the amine, or you can obtain it by ephedrine or pseudoephedrine, which is now a controlled substance because of the fact that people were obtaining ephedrine and changing it into crystal meth. Ephedrine, via various reduction mechanisms, can be taken directly to methamphetamine, or the alcohol can be chlorinated, and then this reaction will dechlorinate it to methamphetamine. So you can see that there are several ways in which something like methamphetamine can be obtained. The alternative Leuchart route, this one, relies on the fact that P2P can produce a racemic product here, but proceeds via a methylformamide, which is what this is, a methformamide, in formic acid. Proceeds via methylformamide in formic acid, that's the reagent, to an intermediate N-formyl methamphetamine. So you can see that in one step via this reaction we've got this, and then that's decarboxylated in actually concentrated hydrochloric acid. This breaks off readily, hydrolyzes and goes to the amine. That actually means that methamphetamine comes in the form of a hydrochloride, and so crystal meth is actually methamphetamine hydrochloride at the end of the reaction. And hydrochloride organic amines can be readily crystallizable, particularly drug-like substances. These are all the some of the accepted names for street names for methamphetamine. Methamphetamine is legally prescribed, believe it or not, for obesity, attention deficit hyperactivity disorder, and narcolepsy. So it is actually a registered drug. Amines and amine alkylation. From ammonia, the availability of the lone pair of electrons on nitrogen allow amines to react as a nucleophile, available pair of non-bonding electrons, towards electrophilic compounds. And what's below is how excess methyl chloride would react with ammonia. And note that the products can be initially isolated as hydrochloride salts on each step, or at most steps. So, if we take ammonia and react it with methyl chloride, and this would actually be in the gaseous phase, we would get methylamine and hydrochloric acid. Now, of course, methylamine is basic and it would react with hydrochloric acid, and we would expect to get a white solid from that reaction if it's in dry conditions. The reaction can be taken further, so methylamine can react with another molecule of methyl chloride to give dimethylamine, which is a secondary amine. So methylamine is a primary amine and dimethylamine is a secondary amine. And then a third equivalent can react to give trimethylamine, which is an example of a tertiary amine. And all of these above would be obtained as hydrochlorides if you so wished, or the reaction can be done in excess methyl chloride to go subsequently to 1 to 2 substitution to 3 substitution, and then finally the final equivalent will give a quaternary ammonium salt, tetramethyl ammonium chloride. And this last step is not an equilibrium per se. It is a pretty much committed step to that type of compound, and quaternary ammonium compounds can be found throughout pharmaceutical chemistry, as can hydrochlorides of tertiary, secondary and primary amines. Now remember, all this is acting as is a framework for you to think about how amines, ammonia and amines react with electrophilic compounds when the electrophilic compound has a leaving group such as chlorine. You can adapt this chemistry to any amine example. What we're going to do here is we're going to look at the synthetic chemistry to produce amines. And one of the common ones that occurs at A level or even previous to A level is reaction of nitro groups. Now, reduction of aromatic nitro groups is the most important route for the production of aryl amines or aromatic amines. And this is often carried out using metal acid combinations such as tin and hydrochloric acid or equivalents. And what you get when you react an appropriate metal with an acid is nascent hydrogen. The hydrogen on reaction of HCl at the surface of the tin, you get bubbles of hydrogen formed from that reaction if you think about the essential inorganic chemistry. Metal plus acid goes to salt plus hydrogen. But at the surface, before the hydrogen molecule is formed, you get a hydrogen radical type species at the surface of the metal, which is highly reducing. So something like nitrobenzene will react with hydrogen equivalents, sufficient hydrogen equivalents to remove the oxygen and to replace those oxygens with hydrogen. We're not going into the mechanism of how the nitro group reduces. That's actually quite complicated. So here we have nitrobenzene going to phenylamine, or aniline as it's more commonly known, and 2 moles of water from that reaction. Reductions can also be achieved by using zinc or iron and hydrochloric acid, or even catalytic reductions. Catalytic reductions tend to be required at elevated temperatures, however, maybe 300 degrees centigrade. So nickel or platinum or palladium in the presence of hydrogen will cause catalytic reduction to take place. Amines can be achieved from carbonyl groups, and we've met carbonyl chemistry in the previous set of lectures, aldehydes and ketones, so don't forget that type of chemistry from that set of lectures. From carbonyl compounds you can get chemistries such as reductive amination, which we saw in the crystal meth preparation. And reductive amination of aldehydes or ketones is possible via their imine intermediates. So we have amines and imines. Notice the change of the letter A to I. And this is a typical chemistry. So we have an aldehyde or a ketone, depending on the nature of R, can interact with ammonia. It forms, because the ammonia attacks the electrophilic carbon and you get a proton transfer, you get something called a carbanolamine after the nucleophilic addition. And this is a carbinol, and a carbinol is a carbon-based alcohol, and an amine on the same functional group, so this is known as a carbanolamine. Carbanolamines are actually pretty unstable, and they will eliminate water from that structure or spontaneously, but also under the influence of acidic conditions, depending on how that chemistry is being performed. And this will form what's called an imine, and this is a condensation reaction because you lose an element of water. This is an imine, and an imine is a ketone aldehyde analog, really, if you think about that chemistry. It's very similar in chemistry to a carbonyl, double bond, sigma bond and a pi bond in a similar arrangement. It's just that the nitrogen has to fulfill its third valency in this position, and that means that we know something about the chemistry of aldehydes and ketones. We should expect imines to undergo a similar type of chemistry. So imines can be reduced, and hydrogen and platinum can reduce the double bond just as it can in aldehydes and ketones when they go to alcohols, and an imine can go to an amine. Practically, reductive aminations, which is what this process can be, achieved by saturating a solution such as ethanol or methanol, in which a hydrogenation is going to be carried out with ammonia, and reducing it in its presence. So in other words, the reaction is in equilibrium, but the reaction is pulled over to product by this final reduction step. These are in equilibria with one another, and the equilibrium is over to this side generally, and then this reactive species is pulled to reduction here. You've got to be careful with reductive aminations, and the ammonia is normally reactive enough to set this equilibrium up well. The reaction can be achieved without ammonia. The reaction can be taken forward with primary amines relatively easily. So a primary amine would add an extra R group here, here and here, and you would get an R group on here and an R2 group. So imagine R2 replacing one of the hydrogens, R2 here replacing one of the hydrogens, R2 here, and then R2 here. So reductive aminations can be achieved with things other than ammonia, primary amines for instance. In nature, enzymes such as glutamate dehydrogenases use this chemistry to synthesize glutamate from alpha ketoglutarate and ammonium ion. So these reactions are done enzymatically. The nitrile group is an interesting one. Nitriles, or cyanocompounds, can be reduced by catalytic reduction or by the use of complex hydrides such as lithium aluminium hydride. And the chemistry can be regarded again very similarly like ketone or aldehyde chemistry. Whereas a ketone would be reduced by lithium aluminium hydride to an alcohol, this system has two pi bonds which can be broken into by the hydride equivalents of here, and it's the H- part of this that's attacking that carbon to move the chemistry towards here. So under certain reaction conditions, lithium aluminium hydride can move a cyano group with enough reducing equivalents here to an amine. To complete that reaction, you would actually have lithium aluminium hydride in, so your cyano group, your cyano compound will be dissolved in a suitable solvent. You would add lithium aluminium hydride to it to do the reaction, and the hydrides attack this species sequentially. And then the final step in the reaction is quenching with acid to finally give an amine. This reaction could also be achieved by hydrogen and a suitable catalyst such as platinum or palladium or nickel. So here we have a typical reaction. Lithium aluminium hydride, the cyano compound is dissolved in ether, and then the reaction is quenched in H2O, or sometimes acidified H2O to finish the reaction off. And we have a production of a primary amine from that chemistry. Or here we have an alkyl cyano compound undergoing reduction with nickel notice at an elevated pressure, which is required to force the reaction to the right hand side. We're just going to go briefly through esterification first, and you'll see why this is the case. So, reminder of esterification. Alcohols can undergo condensation reactions with carboxylic acids to yield esters. This is very common. Alcohol plus acid, carboxylic acid, goes to ester plus water. This is how the chemistry takes place. Often achieved readily under acid conditions, catalytic. It goes via a tetrahedral intermediate, a bit like the carbanolamine intermediate we saw with imine formation, for similar reasons. And then a condensation reaction, removal of water, to give the ester. Now, what we're going to do is look at amidation. Alcohols can undergo condensation reactions, as we've seen, but in comparison, amines will condense with carboxylic acids to afford amides, analogous to esters. This is our carbanolamine-like intermediate, which spontaneously decomposes to give the amide. Now remember, we've seen amide functionalities in the amino acid peptide protein chemistry we did in Cells to Systems. So remember your amino acid chemistry, and in fact there is a set of lectures on amino acid chemistry to extrapolate from the amine chemistry that you can have a look at on the Moodle site for this unit as well, just to remind you of amino acid chemistry, and maybe also to give you a little more insight into what can be done with amino acids. So again, I would encourage you to take a brief look at that topic. Amidation reactions can be achieved by reactions other than reagents other than carboxylic acids. You can have carboxylic acid derivatives such as acid chlorides or anhydrides, and the X group can be quite exotic, so the nature of that leaving group can be quite exotic, and there may be various reasons for doing it. Particularly reactivity of the amine. You may need a particularly reactive carboxylic acid derivative. The amide formation previously is actually often in an equilibrium, and this is why nature, when it's forming amide bonds such as peptide bonds, uses enzymes to achieve that chemistry. Amide formation, when carboxylic acids react with amines, is an equilibrium, and we need to encourage the equilibrium to go to the right hand side so we can form the amide. One of the ways we can do that chemically is to use carboxylic acid derivatives. And the X group variability can be looked at here, I believe. Right, we're going to try to give you a little more chemistry which is relevant to amines that you might come across in the future, and we're putting some stuff together. So what we're going to do is look at a bit of synthesis. We're going to start off with this heterocyclic molecule. This is a heterocycle, a cyclic compound containing atoms other than carbon, so it's a cyclic system with nitrogen in. So this is a nitrogen heterocycle. You can see that this amine is attached to an aromatic, fluorinated aromatic substituent, and we have a dihydrochloride salt. It's a dihydrochloride salt because that would be a stable way of storing that compound. The dihydrochloride occurs because hydrochloric acid would react with that and that. The first step is a Mannich reaction. Now the Mannich reaction is synthetically useful because it can take amines to carbon-based systems very readily, and this is a peculiar compound. This is a convenient source of formaldehyde, and you'll notice that this is like the acetyl functionality we saw when we looked at aldehyde and ketone chemistry and in cells to systems when we talked about carbohydrates. The Mannich reaction allows a reaction between an appropriate ketone, and the Mannich reaction occurs between this compound and this carbon within the compound under the influence of acid. It reacts with this center on the molecule, and you can see that it links the methyl ketone via a bridging group to that amine there. And this link tells you a little bit more about the Mannich reaction. You'll meet the Mannich reaction at a later stage in your course because you do some synthesis with it. Once we've got this heterocyclic ketone, we can oxyminate. So this is reaction with hydroxylamine hydrochloride. This is a classical A-level type chemistry, taking a ketone and making an oxime. Oximes are readily crystallizable, so they used to be used as analytical derivatives of aldehydes and ketones many years ago. But you can take oximes and do something quite nice with them. You can reduce them by lithium aluminium hydride. You can see that this is a imine-like chemistry, and reduction of this system would cause that to split off and this to reduce, and lithium aluminium hydride will take you to a primary amine, which is useful. The compound that we've just produced is a intermediate on the road to making something called neoprosine, and the final step I'm going to show you is an acylation with a heterocyclic aromatic acid chloride under the influence of a basic catalyst, triethylamine, which is also in the reaction. And this is what happens. You get acylation on this primary amine, which is very reactive. The triethylamine there is actually to absorb the HCl that's formed in the reaction. This is neoprosine, and neoprosine is a heterocyclic serotonergic receptor compound, but it also acts at the alpha-1 adrenergic receptor as well, and it has been used for treating sleep disturbances. So, a student from the course that we've just done, a student would be expected to be able to recognise some of the parallels between alcohol and amine chemistry, recognise the fact that amines exhibit similar chemistry to ammonia, utilise simple synthetic procedures to convert a stated type of organic compound to an amine, and identify suitable reagents. All the reagents that we've seen are commonly used reagents, and the majority of them we've met before, particularly in the alcohol, aldehyde, ketone and alcohol chemistries. Recognise that nitrogen can deploy quite different bonding environments in amines, amides, nitro and nitrile compounds, and realise that they can be sp3, sp2 and sp hybridized with different numbers of pi bonds in those functional groups. Compare the chemistry of amides and esters of carboxylic acids at a simple level and extrapolate from generic reactions to specific ones. Remember that the role that the amide linkage plays in structural biological chemistry as well, and appreciate that nitrogen can be part of a heterocyclic ring.